Hello and welcome to today's lesson on nuclear equations, which is part of the atomic structure topic in GCSE Combined Science Physics. So in today's lesson we're going to look at writing out correct nuclear equations for decay processes. So if we've been successful and learned in today's lesson, we should be able to detail the properties of the different nuclear decays. We should be able to describe what occurs in each nuclear decay, and finally write out a full nuclear equation for a nuclear decay. So in today's lesson we're covering the following part of the AQA GCSE Combined Science specification 6.4.2.2 nuclear equations. Now in mathematics we can represent a change with an equation. Now in chemistry we can also represent a change with an equation. Now an arrow is used in chemistry to denote the passage of time for this to occur, and in theory there's no passage of time of mathematics, it's a pure subject. So therefore, because we have no passage of time in mathematics, we represent equations with equal signs, but in chemistry, because there is a passage of time, we use an arrow sign. So in chemistry we balance equations because the total number of atoms before the chemical reaction must be the same as the total number of atoms after the chemical reaction. The total number of atoms must be conserved, and the word conserved means to stay the same. So in chemistry we've got to balance our equations because the total number of atoms before the reaction is the same as the number after the reaction. Now in physics we can also use equations to show the radioactive decay process, and we call this a nuclear equation, and we can use this for either alpha, beta or gamma decay. Now in physics we must be aware that the number of protons and neutrons are conserved in nuclear decay, so therefore we must be aware that the number of protons and neutrons are the same before a nuclear decay as after a nuclear decay. So it's very important we are understanding that the mass number and the atomic number before a nuclear decay is the same as after a nuclear decay. Now in a question you must be able to complete decays correctly for alpha, beta and gamma. So we've got to recognise the nuclear decays for alpha, beta and gamma emission. So if we consider a nuclear equation, we can use this format for either alpha, beta or gamma decay. We can show the nuclei before and the nuclei afterwards. Now remember, this is not a chemical equation as we're only concerning nuclei. So a nuclear equation only look at nuclei decaying. So how can we represent what is found in the nucleus of an atom? Well, in this particular picture you can see that A is the atomic mass, the number of protons and neutrons, Z is the atomic number, the number of protons, and X is the chemical symbol as shown on the periodic table. Now in any nuclear decay equation, the total atomic mass before is equal to the total atomic mass after. The total number of protons and neutrons before is equal to the total number of neutrons and protons afterwards. So in this case 28 before equals 28 after, which makes sense because 0 plus 28 is equal to 28. But as well as that, in any nuclear decay equation the total atomic number before equals the total atomic number after. So the total number of protons before equals the total number of protons afterwards. So here 15 equals 15 because 15 equals 1 plus 14. Now this is important because if atomic mass and atomic number are not conserved, this would mean mass would not be conserved in a nuclear decay, and mass is always conserved. Now the number of protons and neutrons is always conserved in a nuclear decay, which is also a fundamental concept in the idea of chemistry. So let's now look at describing what occurs in each nuclear decay. Well, we've got to be able to write a nuclear equation for each radioactive emission. So let's first consider alpha decay. So 2 protons and 2 neutrons are lost from a nucleus when it emits an alpha particle. So it's important to note that alpha decay causes the atomic mass to decrease by 4, the number of protons and neutrons, and the atomic number, the number of protons, to decrease by 2. So this means the nucleus after the decay has changed element as it has a different number of protons. Now the process of a nucleus changing element due to a nuclear decay is called transmutation. Now alpha decay is therefore an example of transmutation. Now we can represent alpha particles with either the symbol alpha 4, 2 or the symbol helium 4-2. Now just remember the 4 here represents the number of protons and neutrons, the 2 represents the number of protons. Now alpha decay causes both the mass of the nucleus and the charge of the nucleus to decrease. Now as a little bit of a note, an alpha particle can also be considered as a helium nucleus, and each alpha particle is emitted with the same kinetic energy. So let's just consider what's going on. In alpha decay, 2 protons and 2 neutrons are lost from a nucleus when it emits an alpha particle. This means the atomic mass number decreases by 4 and the atomic number decreases by 2. So a new element is formed that is 2 places lower in the periodic table than the original element. So the atomic number has decreased by 2. So this produces a new element as there's a different proton number in the nucleus. So alpha decay causes both the charge and the mass of the nucleus to decrease. So therefore a new element is formed 2 places lower in the periodic table than the original element. Now in beta decay, a neutron changes into a proton plus an electron. Now the proton stays in the nucleus, but the electron leaves the atom with a high energy as a beta particle. So beta decay causes the nucleus to turn one neutron into a proton and an electron. The proton stays in the nucleus and the electron is fired out of the nucleus at a very high speed. So this will cause the atomic number, the number of protons and neutrons, to stay the same because a neutron turning into a proton, but it causes the atomic number, the number of protons, to increase by 1. So this has to happen as the numbers are conserved, so therefore this means that the beta particle must be 0 and minus 1. So in this case, because we've had an extra proton in our nucleus, this means that after the decay has taken place, we've changed element as there's a different number of protons. So this means that we've got a different element after beta decay. So beta decay is another example, along with alpha decay, of transmutation. So beta particles can be represented in an equation with either a beta symbol or an e to the minus symbol for electron, as 0 on the top and minus 1 on the bottom. Now beta decay does not cause the mass of the nucleus to change, but it does cause the charge of the nucleus to increase. Now just as a quick note, a neutron turns into a proton as a proton is ever so slightly smaller than a neutron, so therefore it needs less energy to exist, so the neutron will turn into the proton and also produce a beta particle and electron at the same time. So in beta decay, a neutron changes into a proton plus an electron, the proton stays in the nucleus and the electron leaves the atom with a high energy as the beta particle. So the atomic number has stayed the same, but the atomic mass number has stayed the same, but the atomic number has increased by 1. So therefore a new element is formed that is 1 place higher in the periodic table than the original element. So whilst the atomic mass number stays constant, the atomic number increases by 1. So the beta decay does not cause the mass to change, but it does cause the charge of the nucleus to increase. So a new element is therefore formed as the proton number has changed due to beta decay. So therefore we're changing our charge but not the mass, because a neutron is turning into a proton. Now in gamma decay, there is no change in the makeup of the particles. The unstable nucleus just emits energy. It releases energy from its structure. So gamma decay will only cause the nucleus to release energy. So therefore the atomic mass afterwards of the nucleus remains unchanged and the atomic number of the nucleus remains unchanged. So this means because the number of protons is not changing, the nucleus does not change element after this nuclear gamma decay. So gamma decay is not an example of transmutation. Gamma decay is in fact the relaxation of a nucleus as the protons and neutrons change the way they're arranged in the nucleus as opposed to changing any type. Now gamma rays can be represented in an equation with the following symbol of 0, 0. Now the emission of gamma does not cause the mass or the charge of the nucleus to change. So in gamma decay there's no change in the makeup of the nucleus, it just loses energy. So therefore we can have 2 types of unstable nuclei that can undergo gamma emission. So if it has a star, it means the nucleus has to wait a short time before losing its energy via gamma decay, whilst if it has an M symbol next to it, it means the nucleus waits a relatively long time before losing energy via gamma decay. So at that point we say it's metastable. But remember, in both instances, the atomic mass number and the atomic number have not changed for the nucleus. So the element of the nucleus is unchanged as the proton number is unchanged. So therefore the emission of a gamma ray does not cause the mass or the charge of the nucleus to change. So let's summarize what we've learned in today's lesson. Nuclear equations are used to represent radioactive decay. In a nuclear equation, an alpha particle is represented by the symbol 4,2 helium, He, and a beta particle is represented by the symbol 0-1 E for an electron. Now, the emission of the different types of nuclear radiation may cause a change in mass or charge of the nucleus. So alpha decay causes both the mass and the charge of the nucleus to decrease. Beta decay does not cause the mass of the nucleus to change, but does cause the charge of the nucleus to increase, and therefore you should be able to use the names and symbols of common nuclei and particles to write out balanced equations that show single alpha and beta decays. Now we've only got to think about the atomic numbers and the atomic mass numbers. Now the emission of a gamma ray does not cause the mass or charge of the nucleus to change. So if we've been successful and learnt in today's lesson, we should be able to detail the properties of different nuclear decays, describe what occurs in each nuclear decay, and finally write out a full nuclear equation for a nuclear decay. So I hope you've enjoyed today's lesson looking at nuclear equations, which is part of the atomic structure topic in GCSE Combined Science Physics. Thank you very much for listening and have a lovely day.